All right, so we're gonna start talking about the Hopf theorem. So we've seen before that if we have two functions from xn to yn, where xn and yn are where x is compact, y is connected, and they're both oriented and no boundary. Then we can talk about the degree, and if they're homotopic, we've seen that this implies that the degree of f is equal to the degree of g. So the Hopf theorem is a converse to this question. So it's a question of, does the degree classify the map? If you have a map, two maps that have the same degree, are they actually homotopic? And the answer to this question is in general no. But when y is Sn, is the sphere, then the answer is basically yes, if x is also connected. So the theorem will be the following. So let x be an oriented, compact, and connected manifold without boundary and now let f and g be two functions from x and the dimension n, two functions from x to Sn, such that they have the same degree. Then f is homotopic to g. Okay. So we actually have an if and only if. So f is homotopic to g if and only if the degree of f is equal to the degree of g. So the degree is the only invariant to classify maps from x to Sn up to homotopy. Okay, any questions about the statement? No? Okay, so now let's prove this. The proof I'm going to give here is more in line with the book, Milner's book, Topology from a Differential Viewpoint. Gilliam and Pollack have a slightly different proof. It's a little longer. But anyway, you're welcome to look at their proof too. It's also one of those guided proofs, so they just tell you all the steps to do, I think. So you can read that as well. But this proof that I'm going to give is more in line with the Pontryagin-Thom construction, so that's why I want to give it. It's not much more difficult than the other one. So to do that, we can start by fixing a regular value of both f and g. So let y be a regular value of f and g. And you can always do that because the set of critical values has measure 0. So you can just choose something that's neither a critical value for f nor for g. And I'm going to write Q0. I'm going to let Q0 be the pre-image of y by f, and Q1 be the pre-image of y by g. So these are finite sets of oriented points. And the degree is exactly the number of points in each of these two submanifolds, counted with signs. So the degree of f is basically the number of points in Q0, and the degree of g is the number of points in Q1, where this number here, it means assigned count. Okay? All right, so we want to show that, well, we're assuming that these two are equal. So we assume that the number of points in Q0 is equal to the number of points in Q1 up to a sign. I mean, up to a sign meaning, again, assigned count. So you add all the positive ones and then you subtract, you take the number of positive ones and you subtract the number of negative ones. Okay, so we want to show that we will prove that F is homotopic to G. Before doing that, we're actually going to replace F and G by two other functions that have the same, whose preimage of Y is the same. Okay, so that's the step one. So step one, we will replace F and G by F tilde and G tilde, which are still transverse to Y, and they still have the property that Q0 is the preimage of Y, and Q1 is the preimage of Y by G tilde. Okay, so I'm just going to replace F and G by some functions F tilde and G tilde that I will choose, that will be very specific. Okay, so how do I do that? Well, I start by choosing. So let me draw a picture. So if this is your X, you can Q0 is basically a set of points. Some come with pluses and some come with minuses. That's what an oriented point is. Well, let me put one more here with a plus. And then I can think of another copy of X. And then I have, so this is Q0. And then Q1 will be, so like, let me be plus, plus, and minus. I don't know, something like that. Okay. So what I'm going to do now is I'm going to choose a compact oriented one manifold in the product 0, 1 times X. So here's the product. And I want to choose a manifold, a one manifold whose boundary is exactly the union of all these points. So such that the boundary of C is exactly Q1 times 1, and then 0 times Q0 with the opposite orientation. Okay, so I can always do that. So in this, let me draw it here. So I don't know, I can do this. Here I can do this. And here I can do this. Okay, so this is my C. Okay, so how do I do this? You know, basically, you can always do this with a homotopy. You can think about this, like, you know, because the number of points is the same, then you can kind of connect. You can do one by one, like an induction process. So you can connect all the positive. You can connect the positive point in Q0 to a positive point in Q1. You can exhaust all the positive ones. And then you can exhaust all the negative ones. And if there's a difference, if there are more points in one than the other, then they have to cancel out. So for these plus or minuses that are left in one, you can only basically have them left in one. You create a homotopy that kind of goes like this. Okay, so an exercise. Oh, I also want to assume that that C is transverse to the boundary. So I want to assume that C is transverse to the boundary of 0, 1. times x. Okay, so an exercise is to do what I said earlier, that you can, I draw this picture and then, but I actually do want you to be a little more precise, at least once. Construct C explicitly. Okay, so I already gave you the hints, like you find some homotopy, and you kind of want to make sure that the homotopy never stops, like you have a smooth curve from one point to the other in X, whose derivative is never 0. And that homotopy will give rise to a 1 manifold in the product with 0, 1. And you just have to be a little careful with the points that are left. So you could have either points on Q0 or points on Q1 that are left, but they have to come with canceling signs. And then you have to find the homotopy, and you kind of use half of it to go to, I don't know, 1/2, and then half of it to come back. So you have to be a little careful, but it's the picture, I guess, exemplifies what you need to do. Okay. I mean, if I didn't require this condition of transversality, you could just pick the homotopy to be contained in Q0. But I do want it to be transverse. So you have to go a little bit into the interior, and you have to come back a little bit. Okay. Any questions about this? Do you understand how to construct C explicitly, or do I need to say anything else? Okay, so let me move on. So we will now construct a map, which is going to be a homotopy of maps from X to Sn. So we'll construct a map from the product of 0, 1 with X into Sn. Okay, so I'm not saying what it's a homotopy between. So it's going to be a homotopy between something on the level 0 and something on the level 1. So this, this is a homotopy from H0 dot to H1 dot. But, I'm not telling you what these are going to be. But actually, I'm going to just construct the homotopy. And by definition, this will be my F tilde, and this will be my G tilde. Okay. But what I want to do now is I want to use the C to construct the map. So let's do the following. So first, we can actually look at by, for example, the tubular neighborhood theorem, or something very simple. You can actually construct an embedding of C times Rn into 0, 1 times X. So this is an embedding such that, phi of X0. So you're basically just you're looking at the normal bundle of C, and this tangent, this normal bundle is just an Rn. So you want to take 0 to the same point, the point X, so this the center. And you also want it to be orientation preserving. So d phi du of X0 is orientation preserving. So this will be a map that goes from the tangent space of X0 of C times Rn. If I want to restrict this to the tangent space to Rn itself, this is going to go from T0 of Rn to, oh, no. Actually, I can actually do the whole thing. I don't need to restrict. So this is orientation preserving. I mean, you can just like explicitly choose this. So the way that you choose C, you know, because this point is positively oriented here, or this because you have an orientation here, you can use this orientation to define the isomorphism or the embedding of the normal component to Rn. Okay, so this is pretty, it's basically just the tubular neighborhood theorem seen with the we have to be careful with orientations, but you can do that. Okay, so this is, I can draw a picture here if you want. So there's this is the embedding that I want. I mean, if C is always transverse to the T direction, that's maybe pretty simple, and then maybe it's slightly more interesting in these cases when you have these tubes that go and come back. Okay? So now what you do is so we can choose a diffeomorphism that goes from Rn to Sn and just missing one point, and I'm going to choose to miss the antipode of y, so minus y. So we can find a diffeomorphism, which is the inverse of the stereographic projection, for example. We can just choose it to be the inverse of the stereographic projection. So I wanted to take 0 to y. So you do the stereographic projection with respect to negative y. So here's, if this is your y, this is your minus y, you can do like a stereographic projection like that. And this phi is the inverse map. Okay, so Rn, Sn minus a point is diffeomorphic to Rn. Okay, now we can define H of P is going to be, so psi of U, if P is in the image of this this embedding, so if P is in this tubular neighborhood, then I just take this function, psi. So phi of xu equals P. And otherwise, I just take it to be constant equals to minus y, if P does not belong to the image of phi. Okay, so in other words, like all that you do is you pick a diffeomorphism from Rn to a punctured sphere, and then you use this tubular neighborhood result to say, well, I'm gonna for each slice, so basically at the level x u equals 0, I take this to y, and then the whole Rn that goes around it, I'm gonna map that to the sphere, and I'm gonna miss one point. Okay, so that's the map you obtain. And maybe an exercise is that H is smooth. Maybe not, it's not so obvious that it's going to be smooth along the boundary of this tubular neighborhood, but it is smooth. Moreover, y is a regular value of H and the boundary of H, and the pre-image of y is, can someone tell me to see if you're paying attention or if you're understanding what I'm saying? What's the pre-image of y? So if psi of something is y, then that thing has to be 0. The u has to be 0. So P has to be phi of x0 for some x. And what's that? That's just C. Okay, so the pre-image of Y is going to be C. Okay?
Hello, sir.
Yes?
Would you explain the function h one more time?
One more time. Okay.
Yes,
So
yes.
let me see if I can explain it from the picture. So if I take, say, a slice, oh, it's the same color. If I take a slice here, this would be, I don't know, t times x. Then I'm going to have some points which belong to C. Okay?
Yes.
So the way that I define the function is like this. I look at a neighborhood of each of these points, and a neighborhood of each of these points is basically an Rn. Okay, so then I choose a mapping from Rn to the sphere, which is going to be the inverse of the stereographic projection. And I'm going to take the green points to Y, and then I'm going to map the whole sphere. I'm going to map the rest of each of these little neighborhoods to the whole sphere, missing a point minus Y. So on the boundary here, I'm mapping everybody on the boundary to minus Y. And then outside of these neighborhoods, everything is going to minus Y. Okay, so that's what I do for the slice. So as long as C is transverse to the slice, I do that. Okay?
Okay.
The only reason I have to write this a little bit more carefully is because C is not always transverse to the slice, because there are points, if you have a different number of points on Q0 than Q1, then you will have to have these curves that come back. So you really need to look at the tubular neighborhood of C. Okay?
Okay.
All right, but I hope this little picture helps.
Sorry, I still don't understand why you need to look at the tubular neighborhood.
I mean, the main reason you need to look at the tubular neighborhood is because of these cylinders that come back. Otherwise, you can just apply this argument.
Because with the time you could be hitting the point where it comes back, and there it's not transverse.
Yes, yeah. So if you take this slice, for example, here, that hits this point here, then what do you do?
And with the tubular neighborhood, you can still see the orientation.
Yes, you can look at like an oriented tubular neighborhood. Yeah.
Okay.
It's kind of what this embedding is. Yeah. And then you define, the great thing about the tubular neighborhood is that it's going to be like, you can write the points x, u, where u is in Rn and x is just in C. So the function is going to be defined just on the u coordinate. So it goes to Y at 0, and then when you get to the end of Rn, then it's going to go to minus Y, the end of the tubular neighborhood.
Okay.
Okay. And the point is like, on the boundary of the tubular neighborhood, everything is minus Y. So you can fill in and just define it to be minus Y on the rest. Okay.
Okay. Thank you.
Mm-hmm. So then you have, you have to check the smoothness condition. And then, and it comes just from the stereographic projection. And then Y is a regular value, also not very hard, of both H, boundary of H. That comes from the fact that the boundary of C is transverse to the boundary. And the pre-image of Y is C. Okay? And then now what you can notice is, if you look at the boundary of H, the boundary of H of Y is going to be exactly the boundary of C, which we know what it is. It's just 1 times Q1 minus 0 times Q0. So now basically what I'm saying is that if you define f tilde to be h of 0 dot and g tilde to be h of 1 dot, then the preimage of y by f tilde is going to be q0, and the preimage of g by of y by g tilde is going to be q1. And there is a homotopy, so f tilde is homotopic to g tilde. Okay, so the first step is really like, I don't know what f is, I don't know what g is, I just know what the preimages of a regular value are. So I have this finite set of oriented points. So using just this information, I don't care about what f and g are, I can construct a homotopy from another function f tilde and another function g tilde that have the same preimage. Okay? So the step 2 now is to show that f is homotopic to f tilde and g is homotopic to g tilde. Okay, so I mean, this obviously the second thing is the same as the first thing, so you just have to show the first thing. So what do we know about f and f tilde? The only thing we know is that when you take the preimage of a regular value, you have the same points, and you don't know anything else. So that's what you need to show. You need to show now that if we have two functions such that the preimage of a regular value are the same points with the same orientation, pluses and minuses, then they have to be homotopic. Okay, so so what do we know? We know that y is a regular value of f and f tilde, and that q0 is the preimage of y by f and is also the preimage of y by y. Okay, with orientations. Orientations coinciding. Okay, so now I have to find a homotopy. So first, we need to find, we'll find a homotopy from f to f tilde. And we'll do that in two parts. So first, we will homotope f to a function, I don't know, what do I call it? F prime. No, prime is kind of ugly. Let me do something that's also ugly, but let's put two tildes. Let's homotope f to another function f tilde tilde, which coincides with f tilde in a neighborhood of q0. Okay, so first I'm just gonna homotope f so that it coincides with f tilde in a neighborhood of q0. Okay, so how do we do that? So I first choose an embedding, or I choose a orientation preserving embedding. This is actually a little easier than the previous one. I'm just going to use the tubular neighborhood theorem for q0. So this is just a bunch of oriented points. So I choose an orientation preserving embedding from q0 times Rn to x. That just takes q of x dot to x So I mean, this is the easiest tubular neighborhood theorem. So if this is my Q0, I just take very little neighborhoods like this. Okay. Yeah, but I want them to be orientation preserving. That's the only thing. So the way I map Rn here has to match with the orientation. So if this is a plus, minus, I have to be consistent with that. Okay, so that would mean that I would have E1, E2, E1, E2, and here I would have E2, E1, something like that. Okay, so the image of my Rn is this. Okay, so now I'm going to use this orientation preserving embedding to homotope f to f tilde just in the neighborhood of these points. So now I can let epsilon be sufficiently small such that f of phi u sorry. Yeah, so actually what I'm going to do is away from, if I'm in small enough neighborhoods of y, I can actually interpret my Sn, so the image, I'm not going to write this, but so Sn minus y, again, you can use a stereographic projection onto Rn. So if I am in a neighborhood of Q0, then I'm far enough from negative y. So I can just, think of f and f tilde as taking values in Rn. So yeah, so in this image of Q0 times Rn, I can compose this with the stereographic projection. I don't know, maybe that's easier to do. But anyway, I don't want to change my notes. So what I'm saying is I'm going to keep this function f constant away from these neighborhoods. So I just want to modify it in yeah, I just want to modify it in these neighborhoods. So I can do the transformation just in Rn. Okay, because away from yeah, so I'm going to define. So maybe let me say that first. Sorry. So I can, let me actually do it more properly. So let psi from Sn minus y to Rn be the stereographic projection. And let epsilon 0 be small, such that when you look at f of phi of xu, and when you take psi of that, and you take the inner product with u, this is bigger than 0 for u less than epsilon and bigger than 0. Okay, so you can always do that. And the same thing for f tilde. So this psi and this phi are kind of just maybe adding complication to what you're seeing. But basically just think that when you apply the function f to a point in this tubular neighborhood, that dotted with u is going to be bigger than 0. And that's just because f of q0, f of something in here is going to go to y. Okay, so phi, of course, I'm assuming that phi of y goes to 0. Okay, so this is a simple, maybe if you want, this is a simple exercise. Okay. So the reason I'm doing this is because now I want to do a homotopy. I want to write down the homotopy explicitly from f to f tilde. And I just want to make sure that I stay within this tubular neighborhood. Okay, so we have to choose a bump function too. Rho such that the the support of rho is contained in this ball of radius epsilon around 0, and rho is identically equal to 1 on the ball of radius epsilon over 2. Now you can define the homotopy ft of z, so that's going to be 1 minus rho of u t times psi of f of z plus rho of u t psi of f tilde of z. That's right. So you like interpolate linearly between f of z and f tilde of z, but then you have to use the stereographic projection to look at things in Rn, and then you have to look at the inverse of the stereographic projection to go back to Sn. Okay, so this is if z is phi of xu. Okay, I mean the idea is very simple. All that you need to do is you need to impose this condition to make sure that this does not escape from your neighborhood. Okay, and then you set it to be equal to f of z otherwise. Okay, so anyway, so that's the definition of the homotopy, and it's it's kind of clear to see that f0 f0 is equal to f, and f1, which is what we define to be f tilde tilde, is equal to f tilde in a small neighborhood of q0. So it's exactly going to be equal in this neighborhood given by q0 times this ball of radius epsilon over 2. So there's a little tiny ball where it is equal to f tilde. Okay, and there is this homotopy between the two. Okay, so that's the first step of the homotopy from f to f tilde. So now I have to go and homotope f tilde tilde to f tilde, knowing that it's equal in the neighborhood of q0, so I have to homotope it on the rest. And that's actually the easier part. So now, but any questions before I continue?
I didn't understand the condition on the dot product of C with U. Why do you need that?
You need that because you want this. Sorry, let me remember. Oh yeah, I know. So you actually want the pre-image of 0 of y to always be the same. So you don't want to create any new zeros as you do this. That's the condition that you want.
Okay.
So the problem is that if you could potentially create new zeros at 1. So you really want f1 inverse of y to still be the same. So if you don't know that these guys, when you take the dot product with u, for example, that it's positive, then you could potentially be creating more images for y in here, pre-images of y in here.
Okay.
You see? So that's why you need to be in a really small ball to make sure that the only way to hit 0 is if you're already at 0. I mean, you with psi. Okay?
Okay.
Yeah, sorry, this is a little confusing. I could have written another paragraph, but
It's okay.
okay.
Thank you.
You're welcome. Okay, so now that we have this, we can homotope on
Hello,
the
sir.
rest. Oh, yes.
What was if double tilde?
Hmm?
What was if double tilde?
F double tilde is this homotopy at time 1.
Okay. Right.
Okay? So yeah, namely this small neighborhood is the image by phi of Q0 times B and epsilon over 2. That's where they coincide. Okay, so we now find a homotopy from F double tilde to F tilde. And remember, F double tilde is some function that coincides with F tilde in the neighborhood of Q0. But otherwise, it's completely different. So now it's actually even easier. Now we consider a stereographic projection, but now relative to y. So now we want a homotope outside. So now phi is a stereographic projection relative to y. And I'm going to use it to deform f double tilde to f tilde outside of these neighborhoods. So, and I know that outside of the neighborhoods of Q0, neither function actually attains y. That's why I needed that condition, like to make sure I'm not creating any pre-images of y. Okay? So this is this stereographic projection. And then now I can just define ft of z to be, sorry, I'm using the same letters, but now I'm doing something else. I'm defining a new psi and a new ft to be, so let me call this neighborhood of Q0 V. So V is this phi of Q0 times Vn epsilon over 2, 0. Okay, so my new, well, let me not be so sloppy. H. This is going to be equal to F tilde of Z if Z is in V. So this is the same, F tilde is the same as F double tilde in this neighborhood. And then outside, what I do is I, basically do the interpolation in Rn. So I do 1 minus t times psi of F double tilde of Z plus 1 minus t times psi of F tilde of Z. And then I have to apply the stereographic projection. Okay? And I just want to emphasize that this stereographic projection here is different from this. Okay? It's, if you're looking at a neighborhood, if you're looking somewhere where y is in the image, you kind of take the stereographic projection on the antipode of y. And then here, because you're looking outside of neighborhoods of y, you can take the stereographic projection with respect to y. Okay, so that's basically the end of the proof of Hopf theorem. Okay, so then the conclusion is then F is homotopic to F tilde. And by the same argument, G is homotopic to G tilde. And we had already seen that, by construction, F tilde was homotopic to G tilde. So let me say again, let me say that the big picture of the proof again. The big picture was, you looked at the preimage of a regular value by F and by G. And you have two sets of points that have the same number of points up to counting them with signs. So then what you did is you created this one-dimensional, this compact one manifold in the product of X with 0, 1 that connected all the points, and maybe it had these self-connections too. I think someone wants to join. Yeah. And had these self-connections too. And then using that manifold, we created a homotopy from two functions that had the same pre-images, but maybe were different from F and G. Okay, so that was the first step. And the second step was to be like, once you know that you have two functions that have exactly the same pre-images, how do you define a homotopy from one to the other? Okay? So that's the proof of Hopf's theorem. Okay, any questions? No?
Eu tenho uma pergunta.
Sim.
Não ficou claro para mim. Pode voltar algumas páginas?
Sim, posso. Me fala até onde.
É a hora que você definia... Não, acho que você pode ir mais uma para frente. Você pedia que uma derivada parcial... Aqui, isso. Na parte direita. A derivada parcial de φ com relação ao U fosse orientation preserving.
Sim.
Eu não entendi o que isso quer dizer.
Isso quer dizer que... Bom, aqui você tem um espaço vetorial de dimensão... Aqui você tem uma variedade de dimensão n mais 1. E a imagem dela vai ser uma variedade de dimensão n mais 1 também. Então você quer que a derivada leve... a derivada vai levar um subespaço de dimensão n mais 1, um espaço de dimensão n mais 1, um outro espaço de dimensão n mais 1. E os dois estão orientados.
Tá.
Só a notação que está um pouco confusa. Talvez se você botou parcial aí, a derivada, né? Seria a derivada mesmo. Né?
Ah, desculpa. Na verdade, o que eu queria dizer, de repente eu não fui 100% claro. O que eu queria dizer é o seguinte. Eu coloquei a derivada parcial em relação ao U. Tá bom, deixa eu escrever melhor isso daqui. O que eu queria dizer, né, quando eu faço a derivada parcial em relação ao U, eu tenho um mapa de T0 de Rn. E eu queria, na verdade, me restringir. Eu queria dizer o seguinte, esse mapa, né, vai coincidir com as orientações que você já tem nesses pontos do bordo. Então, na verdade, restrito ao bordo de C, isso daqui vai levar a T0 de Rn em T X de X. Okay, this is the map that I wanted to be orientation preserved. Sorry, I wrote it in a very sloppy way. Okay. But the way to construct this map is by doing the tubular neighborhood theorem and just being careful with the orientations.
É mais ou menos como se você quisesse que aquele mapa bordo de Φ fosse orientável.
Exatamente.
Ah, tá.
Uhum.
Tá bom. Obrigado.
De nada.
Another question, and I don't know if
Yeah.
that's a bit silly,
Só uma coisa.
but
So just one thing. This is exactly what I need to be able to say this line here. That the boundary of H, the pre-image of the boundary of H is exactly the boundary of C with orientations. Desculpa, go ahead.
So if we try to carry this construction, but now like ignore the orientation and just assuming that we have that mod 2 degree being the same, because we can pair up the points in the set where we have more points than the other, wouldn't this construction kind of like carry out kind of the same, but just ignoring the steps where we are worried about orientation? I don't see where the orientation allows us to do this, where if we don't look at orientation, we wouldn't be able to.
The problem is that so what do you want? You want the same number of points, or you want the same number of points with parity?
With parity. The just assuming that the degree mod 2 is the same.
Yeah. So assuming the degree mod 2 is the same, you certainly won't be able to have a homotopy. Yeah, you won't. Let me. Yeah, because you need to choose basically that there's an orientation issue when you fix this diffeomorphism with Rn. Like you won't be able to get a map, a homotopy of maps to Sn if you don't fix the orientation. So let me just say one thing, which maybe will be an interesting exercise. I think maybe this is a proposition. I won't prove this, but I think that what you can prove is if Xn is non-orientable, then the maps from X to Sn are classified by the degree mod 2 up to homotopy. So you need the manifold to be non-orientable, because kind of you basically need to say if you get a particular map onto Rn, you might have to switch the orientation, and you can always do that for a non-orientable map by just taking a loop, or there exists a loop where you switch the orientation. Okay.
Yeah, I guess I'll have to look at this proof more carefully to see where things start failing.
Yeah.
But okay, thank you.
You're welcome. Other questions? No. Yeah, let me just say, I think, to be honest, this is the place right here, this more technical stuff, this is the place where you actually need the orientation. So look into this part right here. Okay, I think this is what you won't be able to do. Like when you try to do this homotopy without caring about orientations, then you will not be able to have these both positive. And as you homotope you might be creating other points.
Okay, yeah, that makes sense actually. Thank
Yeah,
you.
but this is the one part where you really need this positivity. Okay, all right, so let's keep going and let's talk about something that is more general than this, and it's called the Pontryagin-Thom construction. But the way that I set this up, maybe everything is going to be, apart from the definitions, the proofs are going to be kind of simple. But let's talk about it. Are there any other questions about this proof before we continue?
Eu tenho uma pergunta.
Sim.
Uma vez eu tinha visto o teorema de Hopf, só que ele era tipo, ao invés de x qualquer, era só de SN, SN para SN.
Sim.
Aí eu queria saber se a prova de SN para SN implica a prova para x qualquer compacto, ou não.
Olha, eu acho que o enunciado... Eu acho que o enunciado não implica o outro enunciado de uma forma muito trivial. Talvez tenha alguma forma um pouco complicada de mostrar isso, mas eu acho que a demonstração de SN para SN não é muito mais simples do que essa. Dá para fazer uma demonstração sem usar cobordismo, né, que basicamente eu usei implicitamente aqui. Mas é o mesmo teorema, na verdade. É só você perceber que a demonstração de SN para SN funciona também para uma variedade, quando o domínio é uma variedade qualquer que seja conexa e compacta e orientada.
Entendi. Tá bom. Obrigado.
De nada. Okay, so let's talk about the Pontryagin. And actually here it's a similar story, the Pontryagin-Thom construction, because I think the Thom originally constructed something like this, but just for maps of spheres, and Pontryagin generalized this for other manifolds. So the setup here is, you take xn to be an oriented, compact manifold, and you don't have to assume it's connected quite yet. So we want to classify maps from X to Sm up to homotopy. So now we want to classify maps onto this to the sphere, but now the dimensions don't have to be the same. So M can be different from N. Okay. So first of all, an observation is that if N is less than M, then you have a bunch of points. The image cannot be everything because the set of regular values is dense. So then the, let me call this F, then F is not surjective. So since it's not surjective, you can use the stereographic projection based on a point where the function doesn't reach, and then you can homotope F to a constant map. So F is homotopic to a constant map. Okay, so if it's not surjective, then basically F can be seen as a map from X to Rm. So then you can homotope it to a constant map. So it's not very interesting to look at the case when N is less than M. So we just assume from now on that N is bigger than or equal to M. Okay. The case N equals M, we already kind of talked about. It's the statement of Thom's theorem, not Thom's theorem, the Hopf theorem. And if X is not connected, then basically what you have is you have a degree for each connected component. So I mean, it's kind of, you just split the problem into by the connected components of X. That's why I'm not going to impose the condition of being connected. That's the only reason you need that is that you need that to be able to connect all the pre-images. So you need to say that, if you have a degree, then you have a cobordism. Anyway, I'm going to talk about this now. Okay, so before, let me say before we do that, let's see what kind of degree theory we would have in this case. So let's say that you have F and G, two maps from X to Sm. So the first thing is you see that, when you take a regular value, if Y is a regular value, of both F and G, then we can look at the pre-image of Y and by F and by G. But now these guys here they're no longer points. They are n minus m dimensional manifolds. And the question is, how do we compare them? What can we say? What can we expect them to be? What kind of relationship can we expect? So if there were points, then it was kind of easy because we could just count them with orientations, and we can just say, we can define a degree, and we can even conjecturing Hopf's theorem is not that hard. But in this case, if the dimension of X is bigger than M, then these are higher dimensional manifolds. So what could you expect? You could maybe expect them to be diffeomorphic, but that actually is going to turn out to be very strong. So to give you a hint of where we're going with this, let's just assume that, for now, that F is homotopic to G. And let's see what relationship we're going to get between these two. So what happens is that, we can again, so we can call HT a homotopy. Well, let me write H from 0, 1 times X plus M, a homotopy from F to G. Okay? Oops. And let's suppose Y is also a regular value of H. So suppose H is transverse to Y. Okay, now what we can do is, we know that F is transverse to Y and G is transverse to Y. So we can take the pre-image of Y by H, and we know that's going to be a manifold with boundary, and the boundary is going to be given by the difference of these two manifolds. So now we can look at the pre-image of Y. This is a manifold with boundary. And the boundary is exactly the pre-image of Y minus the pre-image of Y by G minus the pre-image of Y by F. So this is the relationship that we have between these two manifolds. Okay. If they were zero-dimensional manifolds, then having the same number of points is the same as being the boundary of some one-dimensional compact manifold. I mean, assuming the domain is connected. But in higher dimensions, this is the relationship that that's kind of at the core of homotopy. That's the relationship of manifolds that relates to homotopy of functions. And this is called a cobordism. So I can write a definition. You say Q0 and Q1 submanifolds. They are cobordant if there exists, let's say everything is compact. If there exists a compact submanifold W of the product 0, 1 times X, such that, let's assume some things, such that the boundary of W is 1 times Q1 minus 0 times Q0. That's what it means to be cobordant. And W is called the cobordism. Okay. Yeah, so what we saw here is that if F is homotopic to G, then the preimage of a regular value is cobordant to the preimage of a regular value by G. Okay, so then these manifolds, they are cobordant. Okay, and now maybe the converse question is being cobordant enough to actually to being homotopic? So, say that you know these guys. So I guess it's the opposite direction. So we saw this. And now the question, what about this direction? Is it true? And this, basically, in the case of degree theory, if you think about that, what I've said so far is this cobordism is basically degree theory mod 2. Because it's the comment by who I forget, I don't remember who was talking before. I didn't catch the name. Was it Yuri who was talking about doing this proof in mod 2?
Miguel.
Miguel, sorry. Miguel?
Yes?
Oi?
Yes?
Yeah, so it was Miguel who was talking about this. Yeah, so basically the question would be, if I have two functions and I look at the preimages of the same regular value and they are cobordant manifolds, so I have this cobordism like that, can I actually prove that they are homotopic? Is this the right condition? And the answer is, well, let's look at just the dimension 0 case. In the dimension 0, the preimage of two regular values, so if X and SM have the same dimension, then being cobordant as points is the same thing as basically having the same number of points mod 2. Because, if I have, I can draw that picture, if I have same number of points mod 2, then I can find, I can connect like this. But we actually needed a little more for Hopf theorem. We didn't just need mod 2, we actually needed the numbers to be the same with signs. So this is giving us a hint that in higher dimensions, we need more than just this cobordism. Okay? So that's what I'm going to talk next. So what replaces this condition of the oriented points in Hopf theorem? Okay, before I keep going, are there any questions about this? What I said so far? Does everybody understand what a cobordism is?
Yes.
Okay.
É,
Maybe I should draw a picture. Yeah.
Então, essa definição é equivalente a dizer que, vamos dizer assim, o bordo de W é meio que a união de duas variedades, né?
Exatamente. Mas a união onde uma está acontecendo com a orientação contrária na fatia 0 e outra está acontecendo com a orientação correta na fatia 1.
Ah, ok.
So, for example, this is a cobordism. Okay. All right, so now we need to talk about something called the framing. So definition. Let Q be a k-dimensional manifold, submanifold of X. So let Q be an oriented compact submanifold. Actually, it doesn't have to be oriented to talk about this, but anyway, let's do it anyways. A framing on Q is a choice of trivialization of the normal bundle. So when you choose a way to trivialize a normal bundle, that's called a framing. So this is equivalent to a choice of frame. Well, let me say what it is instead. It's equivalent to a choice of vector fields. So you choose basically a basis for the normal bundle at each point. So a choice of n minus k vector fields along Q, such that at each point, these are a basis. These form a basis of the normal bundle to Q. And again, as I said before, you can either choose a Riemannian metric and think of the normal bundle as being the orthogonal complement of the tangent space at each point, or you can just think of, as some more abstract quotient. You can think of the quotient of Tx by Tq, or you can take any complementary subbundle that's complementary to Tq. Okay, so this is what a framing is. So for example, let's do a very concrete example. Let's take a knot in S3. So I'm going to take the simplest knot which I can think of, which is called the unknot. Unknot. So I'm going to write everything explicitly this time. This is going to be cosine of t, sine t 0 for t in 0 to pi. So it's just this knot. And now I'm going to choose a framing. So what is a framing? Let's look at the normal bundle. I need to choose for each point along on this knot, I need to choose a basis of the normal bundle. So I'm going to choose the following thing. I'm going to choose V1 to be this direction that points outwards, and V2, the direction that points up. So V1 is going to be cosine of t ddx1 plus sine of t ddx2, and V2 is going to be ddx3. Okay, so this eta, V1, V2, is the trivial framing on K.
Professor,
Oi.
Esses frames não são locais? Tipo, o fibrado normal, ele sempre é trivial, acho?
Não. Eu não falei que um framing sempre existe.
Ah, tá.
Isso é uma observação que eu vou fazer depois. Yeah, so it is not true that every submanifold admits a framing. I'm just saying what a framing is. Okay. Yeah. So if the normal bundle is not trivializable, then it doesn't admit a framing. So for example, if you take the Möbius band, the Möbius band is not oriented, but if you take the Möbius band in R3, it won't have a framing because the normal bundle is not orientable. But you can find examples of, or everything's oriented where framings don't exist, but you have to look in higher dimensions. Okay. Okay, so by the way, this is in R3, which is embedded into S3, which is the same as S3 minus a point. Okay, but let me just tell you some other framings. So you can, for example, you can consider eta m. So you can think of, instead of this taking this basis that's just going like this kind of trivial framing, what you can do is, as you rotate along this unknot, you can kind of rotate, as you go along the unknot, you can rotate your basis. And you can do like a full turn, for example, or several turns. So you can write, for example, cosine of mt times v1 minus sine of mt times v2, and then sine of mt times v1 plus cosine of mt times v2. So this is a vector field at the point cosine t sine t 0. So as your t goes from 0 to 2 pi, so as you go around the unknot, you take your canonical basis in the space and you rotate it. Okay, so this you can do this for any m in Z. And an interesting exercise is that these framings are all different, or they're non-isotopic for different values of m. This is not obvious, but you can prove that.
Vinícius,
Oi.
tem alguma classificação desses frames para aqueles lane spaces?
Framings para lane spaces.
É.
Como assim? Framing é de uma subvariedade.
Tá, mas... Tá.
Se você tiver um nó dentro de um lane space, sim, você deve estar pensando nessa questão por algum problema que você está pensando, mas você precisa te explicar um pouco melhor qual é o problema.
Tá.
Porque o framing de um lane space não faz sentido.
Eu tava pensando se eu trocasse... Que você tá falando da taxa de Möbius, né, que não admite.
Sim.
Então, tem algumas combinações de inteiros ali dos meus lane spaces que pode dar alguns projetivos ou algumas coisas assim.
Aham.
Eu tava pensando se tem algumas combinações de inteiros que determinam, que falam, se eu tiver 2, 2, então essa subvariedade admite um framing.
Qual subvariedade?
Aqui der, por exemplo, eu tava pensando nesse sentido. De combinação, se dado 2 inteiros, se esses 2 inteiros me falam se admite um frame ou não.
Não, eu acho que você precisa falar de mais alguma coisa. Because the frame, so I think you're getting framings and orientations a little confused. So the orientation is one thing. The framing is only something that a submanifold has. So you need to talk about the ambient manifold and a submanifold to talk about the framing. And by the way, the lane space, RP3 is orientable. So the lane space that gives out RP3, that's an orientable manifold still. But maybe what you're saying, that you're thinking about some problem that does make sense, but you need to think about which submanifold in the lane space you want to consider. The lane space is a closed manifold that, it's a quotient of S3. So, okay. So one interesting exercise, I mean, it's not very hard, but I guess it's interesting, is that every knot in S3 admits a framing. I mean, the easiest way I know how to do this is using algebraic topology, but maybe someone can think about a smart way to do it without algebraic topology. But if you have a knot in R3, then you always have a framing. And the framings up to isotopy are classified by an integer. Okay, so why is that? Basically, you can think of a framing of a knot the following way. So, you have a knot. I don't know, say you have a knot like that. It's a trefoil knot. Then you can think of a framing as, you choose a basis, V1, V2. But actually, all you need to do is choose V1, because if you know that your knot is oriented, I mean, if you pick an oriented knot, the ambient space is oriented. So if you pick V1, the other guy is just fixed for you by the orientation. So all that you actually need to fix a framing is one vector field up to isotopy. Okay, so if you pick one vector field, that's actually the same as you can kind of exponentiate the map, the knot. We can exponentiate this vector field, and you obtain another knot that kind of follows this closely. I mean, I'm not going to do crossings well here, but basically, you can think of a framing of a knot as another knot that's that doesn't intersect the original knot in this tubular neighborhood of the knot. Okay, so that's another way to see a framing. And basically, if you have one such knot, you can act on the framing by just kind of doing more twists of this other knot around the original knot. And that's the same as taking your framing and rotating.
Aquilo que são classificados não são os nulls, né? São
os framings.
Os framings.
Yeah.
Tá.
Não, classificar nó é uma pergunta muito mais complicada, mas dado um nó, a gente pode falar da classificação dos framings. Então, os framings são basicamente um espaço afim sobre Z. Não existe um framing trivial, a não ser no caso do one knot, mas não existe um framing óbvio, trivial. Mas existem alguns framings interessantes. Existe o que eles chamam de blackboard framing, que é você pegar a projeção do nó e você simplesmente andar para a direita ou andar para cima, tanto faz. But anyway, I'm not going to talk too much about knot theory. I think I'm not going to say anything else. But I just wanted to remark that not all manifolds, not all submanifolds have a framing. Admit a frame. But the pre-image of a regular value does. So that's kind of the moral here. So now let f be a function from x to Sm, and let y be a regular value. Then f, the pre-image of y, admits a natural framing. And what's this natural framing? It's given as follows. Well, if you look at the derivative of f at a point x on the pre-image, we know this is a surjective map from Tx to Ty of Sm. This is surjective. But we know that the kernel of this map is actually the tangent space to, well, let me call this Q, the pre-image of Y. We know this is just the tangent space to the submanifold. So that means that when you restrict it, the restricted derivative to the normal bundle, you still have a surjective map. But these guys have the same dimension, so this is going to be bijection, isomorphism. For every x in Q. So now we can fix a given oriented basis. You can just fix an oriented basis of the tangent space to Sm at this point, and you take the pre-image of that for every x. So you fix an oriented basis V1 through Vm of Tysm, and we let eta be V1 be the pre-image dfx inverse of V1, dfx inverse of Vm, and this is a basis of the normal bundle at Q. Okay? So that's the framing. All right, great. So not every submanifold is framed, but the submanifolds that come as pre-images of regular values of functions are framed. And now I just have to introduce one more concept, which is a framed cobordism. So, so if Q0 and Q1 are framed submanifolds, we say that W is a framed cobordism from Q0 to Q1 if. So first of all, I'm going to assume that this cobordism is kind of constant near 0 and near 1. You can always do that. So if you intersect W with 0 epsilon, and then 1 minus epsilon 1 times x, you obtain 0 epsilon times Q0 union 1 minus epsilon 1 times Q1. So like, you know, if your frame cobordism, it starts kind of constant and it ends kind of constant, and all the action happens in the middle. Okay, but what does it mean for the cobordism to be framed? It just means that there exists an framing on W. So, you know, it's just it's the same definition as before, such that eta restricted to 1 times x is equal to eta 1. So these are framed, and the framings are eta 0 and eta 1. And then eta restricted to 0 times x equals eta 0. So it's exactly what we'd imagine, you know, this W, the normal bundle of W has the same dimension as the normal bundle of Q0 and Q1, and W, when you restrict it to the 2 pieces of the boundary, the normal bundle is exactly the same. So if you assume that the W is kind of trivial near the ends, and that, you know, the metric that this direction is orthogonal to this direction, then the normal bundle of W restricted to 1 times x is equal to the normal bundle of Q1, or there's a obvious isomorphism. Maybe I should just write it. It's the normal bundle. No, let me just write it. It is. It's really this. Okay, so a framing on W is just a frame cobordism is just a cobordism that has a framing that restricts to the cobordisms eta 0 and eta 1. Okay, and an exercise is to show that being framed cobordant, actually being cobordant and being framed cobordant are equivalence relations. And finally, let me state the main theorem, and I can talk about the proof a little bit on Thursday. The theorem is that if you have two functions from x to Sn, then f is homotopic to G if and only if the preimage of a regular value is cobordant to the preimage of regular value of G tilde, where f is transverse to y and G is transverse to y tilde. Okay, so that's the idea, that's the most general theorem for the Pontryagin-Thom construction. So if you want to check whether two functions are homotopic, all you need to do is you look at at the preimage of regular value of one and a regular value of the other. And you look at the manifolds that you obtain. These are called the Pontryagin manifolds. These are, sorry, I forgot the most important thing, just to say it's framed cobordant. Okay, so you look at these framed manifolds, submanifolds, and you have to check if they're framed cobordant or not. And if they are, then the original functions will be homotopic, and if they're not, then they are not going to be homotopic. Okay, sorry for going a little over time. I started a little later, but I will continue this on Thursday.